Hey folks, in this video we're going to look at a really interesting way to generalize the classical determinant and adjoint to more than one linear map. Before watching this video, you may want to watch my prior videos on determinants, which cover the basics, but we'll also review what we need here. Let's get started. Throughout this video, we let V be an n-dimensional vector space over the field F. For simplicity, we assume that F has characteristic 0. If you want, you can take F to be the real or complex numbers. We also let delta be a non-zero n-dimensional determinant function on V. To start, we let phi be a single linear map on V and recall some basic definitions. The classical determinant of phi is the scalar det phi, satisfying the equation seen here for all vectors x1 to xn. We know that there is such a scalar by the universal property of delta. Specifically, the left-hand side of this equation, when viewed as a function of x1 to xn, is multilinear and alternating, so is an n-dimensional determinant function on V, which must be a scalar multiple of delta by the universal property. The scalar is uniquely determined by phi. The classical adjoint of phi, sometimes also called the adjugate or the adjunct, is the linear map adj phi satisfying the equation seen here for all vectors x1 to xn. Notice how the n-1 phi's on the left-hand side of the equation become the single adj phi on the right-hand side. This property uniquely characterizes the adjoint. We take a moment to recall how we arrived at this definition. To construct adj phi for a fixed vector x, we define big phi as seen here. Notice that big phi is multilinear and alternating since delta is. So big phi is an n-1 dimensional determinant function on V. From a prior video, we know this means there is a unique vector x prime satisfying the equation seen here for all vectors x1 to xn-1. We write x prime as adj phi x. It follows from these equations that adj phi is a linear map uniquely determined by phi, which satisfies the equation on the previous slide. If delta of x1 through xn equals 1, then we have this simple formula for the determinant, and this slightly less simple formula for the adjoint, where x appears in the ith position of delta on the right-hand side. These formulas can be used to actually compute determinants and adjoints if you ever forget that computers exist. The determinant and the adjoint are related by this important classical theorem. Here iota is the identity map. This theorem is essentially equivalent to Laplace's cofactor expansion formula for the determinant, as well as Cramer's rule. As a corollary, if the determinant of phi is non-zero, then the adjoint yields the inverse of phi, as seen here. The question arises, can we somehow generalize these ideas to more than one linear map? Interestingly, the answer is yes. We start with the determinant. Consider the function big psi defined as seen here for n linear maps phi1 to phi n of V. This is just like the function used in the definition of the determinant, but with n linear maps instead of 1. Now big psi is clearly multilinear since delta is, but it's not in general alternating, so it's not in general a scalar multiple of delta. However, as we saw in a prior video, we can solve this problem in a standard way using something called the alternator. We obtain an alternating function big psi a by applying the alternator to big psi, which sums over all signed permutations of big psi. Expanding this definition, we find that big psi a is given by the formula seen here. Notice that the vectors x1 to xn are being permuted on the right-hand side. Equivalently, we can permute the linear maps instead of the vectors, in which case the sign factor is eliminated since delta is alternating. Since big psi a is multilinear and alternating, it's an n-dimensional determinant function on V, so it's a scalar multiple of delta by the universal property. We write this scalar as det phi1 to phi n. This leads us to a definition. The mixed determinant of the linear maps phi1 to phi n is the scalar satisfying the equation seen here for all vectors x1 to xn. This scalar is uniquely determined by the maps phi1 to phi n. Notice this definition closely resembles the definition of the classical determinant seen earlier. In fact, if we take all of the phi's equal, then up to a factorial we recover the classical determinant. So this definition really is a generalization. If delta of x1 through xn equals 1, then we have this formula for the mixed determinant. It's easy to see that det is multilinear and symmetric as a function of the phi's. That means we can rearrange the phi's any way we want, and we still get the same mixed determinant. If we don't want to sum over n factorial terms, we can use this theorem, which expresses the mixed determinant as a sum of signed determinants of sums of the linear maps. Here, bracket n denotes the set of numbers 1 through n, and the exponent of the sign factor is the size of the complement of the subset alpha. The outer sum here has only 2 to the n terms, down from n factorial. Turning things around, we can also express the determinant of a sum in terms of mixed determinants. For simplicity, we state this theorem for a sum of 2 maps, but it can be generalized to more than 2. From the mixed determinant, we also obtain a natural generalization of the characteristic polynomial of a linear map. The mixed characteristic polynomial of the linear maps phi1 to phi n is given by the definition seen here, where the lambdas are non-commuting indeterminates. Remarkably, we obtain a generalization of the Cayley-Hamilton theorem, which says that the linear maps satisfy their own mixed characteristic equation. This reduces to the classical Cayley-Hamilton theorem when all of the maps are equal. Isn't that slick? Recalling that the classical determinant is just the factor by which a linear map scales n-dimensional oriented volume, when working over the reals that is, we might wonder whether there is a natural geometric interpretation of the mixed determinant. The answer is yes. Mixed determinants are closely related to a concept called mixed volume in convex geometry. But we won't dive into that in this video because we've got too much other interesting stuff to cover. Just as we generalize the classical determinant, we can also generalize the classical adjoint. For a fixed vector x, consider the function big phi defined as seen here. This is just like the function used in the definition of the classical adjoint, but with the n-1 linear maps phi1 to phi n-1 instead of just 1. Big phi is multilinear since delta is, but it's not in general alternating. Again, we can solve this problem using the alternator. We obtain an alternating function big phi a by applying the alternator to big phi, which sums over all signed permutations of big phi. Since big phi a is multilinear and alternating, it's an n-1 dimensional determinant function on V. Again, we know there is a unique vector x prime satisfying the equation seen here for all vectors x1 to xn-1. We write x prime as adj phi1 to phi n-1 x. It follows that adj phi1 to phi n-1 is a linear map uniquely determined by phi1 to phi n-1. This leads us to another definition. The mixed adjoint of the linear maps phi1 to phi n-1 is the linear map satisfying the equation seen here. The sum on the left-hand side of this equation comes from the function big phi a on the previous slide, where we've again eliminated a sign factor by permuting the linear maps instead of the vectors. Although it's slightly more complicated, this definition closely resembles that of the classical adjoint. And if we take all of the phi's equal, it reduces to it, up to n-1 factorial. If delta of x1 through xn equals 1, then we have this formula for the mixed adjoint. On the right-hand side, x is in the sigma inverse nth position of delta. Again, this is a little bit more complicated than the classical adjoint. It's easy to see that adj is multilinear and symmetric, so we can rearrange the phi's as we please. With the mixed adjoint and the mixed determinant now in hand, we can look for generalizations of classical theorems involving the two. First, we find this strikingly beautiful theorem relating the mixed determinant to the mixed adjoint. This generalizes the theorem we saw earlier relating the classical determinant to the classical adjoint, as you can verify by taking all of the phi's equal. It can be proved using the Grube-Vanstone identity from mixed exterior algebra, for example. I covered the matrix version of that identity in a prior video. This theorem gives rise to a generalization of the Laplace cofactor expansion as well as a generalization of Cramer's rule. It can also be used to prove an analog of the invertibility result for classical determinants. For simplicity, we suppose that the linear maps phi1 through phi n have rank 1. If their mixed determinant is non-zero, then we can define the linear maps pi I seen here. These maps come from the right-hand side of the first equation in the theorem after dividing by the mixed determinant. It follows from the theorem that the pi I are rank 1 projection operators which provide a resolution of the identity. So the space V decomposes as the direct sum of the one-dimensional images of the projections. In a certain sense, this can be viewed as a generalization of the invertibility of a single linear map to more than one linear map. Everything that we've covered so far carries over to matrices using the relationship between matrices and linear maps. I won't bother translating all of the definitions and theorems, but I'll note a few interesting connections. First, historically, the mixed determinant of matrices was called a cubic or three-way determinant, because you can arrange the entries into a cube in 3 dimensions. This is part of a much larger theory. It's also called the mixed discriminant, and it's sometimes divided by n factorial. Notably, the mixed determinant of matrices is just the trace of the box product of the matrices. I covered the box product in a prior video, so be sure to check that out. The box product can also be defined for linear maps using exterior algebra, in which case this theorem can be stated for maps. Taking all of the matrices equal shows that the classical determinant of a matrix is just the trace of its top compound power, which is a familiar result. What about the mixed adjoint? It turns out that the mixed adjoint of matrices is also related to the box product, through the Poincaré dual operation. In particular, the classical adjoint of a matrix is just the dual of its n-1st compound power. What exactly is the Poincaré dual operation? Unfortunately, I don't have time to dive into that right now, but I plan to cover it in a future video, so stay tuned. That's all for this video. Here are the references I used while making it. Thanks for watching.